Okay, any question here? You see, the main idea, okay, we have all these derivations, etc. But the main idea of the Noether theorem is if you have a continuous symmetry, then there will be a conserved quantity corresponding to that symmetry. And in fact, we will also, okay, let's first finish this discussion of the momentum. But the other way around, it will also be true. If you have a conserved quantity, well, there is a symmetry corresponding to that conserved quantity. So this is a two-way equality. If you have a symmetry, there is a conserved quantity. If you have a conserved quantity, there will be a symmetry. And when what we call momentum is actually just the, how to say, the conserved quantity corresponds to translations of space and time. Now, energy will correspond to translations in time. Three momentum will correspond to translations in space. Now, another part of your homework, let's consider a symmetry. Phi prime of x will be actually phi of x. Let me put the components. X mu is phi of x mu plus omega mu nu x nu, such that x mu under this transformation actually goes to x mu. You see, this is the condition of the Lorentz symmetry. Lorentz symmetry are all transformations of the coordinates which do not change the forward distance. And an infinitesimal transformation I can write in this form. If this transformation is a subgroup of Lorentz symmetry, you see, translations contains Lorentz symmetry, is a part of Lorentz symmetry. But translations you cannot write in this form. But what you can write in this form will be the boosts and rotations. What will be the corresponding conserved quantity? What are their expressions? Just find the corresponding expressions for the there will be boosts and there will also be rotations here. And while we are making the derivation, just don't forget to use this expression to derive certain constraints on omega mu nu. This will tell you that omega mu nu should be either symmetric or antisymmetric. Where? Here. Oh, okay, so let me write it a bit more explicitly. Well, the transformation will take x mu to x mu plus omega mu nu. This should be equal to x mu. Of course, there will be corrections of the order of omega squared, which we ignore. This is the infinitesimal form of this translation symmetry. Okay, so we have the momentum. You see, here we have the T mu nu. And to calculate pi, T0i, but T0i, well, the last term does not really contribute. This will be equal to d cubed x del L by del 0 phi del I of phi. You see, this is pi I, pi of phi, pi of x. It's just the moment. Well, you see, I said that the conjugate momentum and linear momentum, they are not they are not the same thing, but you see here that they are also related. Well, we know the expressions of our fields phi. Phi of x was given by as an integral over the momenta. 1 over 2 ek under the square root. We have a of k e to the power minus I k x plus, no, I used phi. Phi of k and phi dagger of k. This was our field. Well, again, the rest will be just straightforward but kind of boring derivation. But let's do it once. So pi becomes d cubed x. Now the conjugate momenta is just the time derivative of this expression, so it becomes d cubed k1. Let me call the momentum integral k1. 2 pi cubed 1 over square root of 2 ek 1. The time derivative will just bring me a minus I ek1. Phi of k e to the power minus I k x minus phi dagger of, these are all k1s, e to the power I k1 of x. This is the momentum, conjugate momentum. Then I have d cubed k2, 2 pi cubed, 1 over square root of 2 ek2. This is from the definition of the field. Now these derivatives will just bring me factors I, ki, the I component of the 3 momentum, k2, I will just jump a couple of steps. You see, if you look at these expressions, all of those expressions, the only x dependents are in the exponents. When I multiply them and integrate over the x values, they will bring me Dirac delta functions. And using those Dirac delta functions, I will evaluate the k2 integral. And I will just, instead of k1, I will just write k1. So let's see, this is d cubed k. Instead of k1, I will just write k divided by 2 pi cubed. 1 over, you see, in all these products, in all possible combinations, k1 and k2, 3 vectors, they will either be equal to each other or equal to minus one another. But whether k1 is equal to k2 or k1 is equal to minus k2, the energies will be the same. Energy of k corresponding to k1 is the same as the energy corresponding to minus k1. So these prefactors will always be 2 ek minus I ek. These will always be the same. Now this is k2. Now let me just multiply them. Now the first term, and keep in mind that these fields here in this expression, they are at the same time. I'm not writing it explicitly, but in these expressions, they will be always at the same time. So, and k1 0 and k2 0, they are just ek1 and ek2. They're also equal, whether the 3 components are equal, pointing in the same direction or in the opposite direction. So let's see. The product of the first two terms, it will give me a Dirac delta, a 2 pi cubed, but I also cancel 2 pi cubed with one of these 2 pi cubes in the here. So just a Dirac delta K1 plus K2. Well, let me write the Dirac deltas. I already evaluated it, by the way. So I have phi of K1, phi of K2, and e to power minus I minus 2e k x0. I just evaluated the remaining x integrals. Then I have minus phi of K1, phi dagger of K2, Dirac delta cube, K1 minus K2. Okay, this is the nice terms. Let me just use the K for all of them. I evaluated the delta integral already. Then I have minus phi dagger of K1, phi dagger of K, phi of K, this term and this term. And then I have the product of the last terms. By the way, here I have a, let's see, this is, in the first term I have a K2i. Let me write the K2i. Here I have a Ki. There's a, okay, this I cancel this minus I. So there's no minus I over here. Here there's a Ki, here there's a Ki. In the last term I also have a minus K2i, phi dagger K1, phi dagger K2, e to power I 2ek x0, and then I have a Dirac delta cubed K1 plus K2. Yes, this should be it. Which is equal to, okay, let me write everything explicitly now, 2 pi cubed. Well, this will cancel this one. There's a factor 1 over 2. I have minus Ki phi of K, phi dagger of K, plus phi dagger of K, phi of K. Okay, this is almost nice. Well, I don't like that minus sign, but we will see where that came from. I mean, maybe I made a mistake somewhere, we will check later on. Plus, I have a d cubed k divided by 2 pi cube, 1 over 2. I have again minus Ki over 2, phi of K1 phi of E of K and K, and then phi of E of K and minus K. And then I have e to power minus 2i ek of x0, and then plus phi dagger of E of K, K, phi dagger of E of K minus K, e to power 2i E of K x0. Okay, the first term is what okay, let me first check that minus sign. Okay, this is the correct expression we have. No, okay, no, everything is fine. Now, what I am kind of puzzled is the last term, the second integral. I didn't expect that term, but well, that's what we obtained. Now, the first term again makes sense in the sense that, okay, this is essentially the number operator up to some constant, plus number operator plus a constant. That additional constant gives us an infinite contribution, but fine. So what we will be actually interested in is not this operator, but its eigenvalues, or how those eigenvalues change when we create a particle or annihilate a particle. That is what we will be interested in. So in that sense, that's just the number operator multiplying by the momentum. So you just have the number of particles which has the momentum ki, you multiply it with ki and sum over all the k. So that gives you the total momentum of your system. That is what we expected. Again, maybe up to a minus signs. But those minus signs will be essentially, you see, p mu with the upper index. This is actually e minus p. And p mu with the lower index, it should be EP. Again, let me put a question mark. So that minus sign is probably whether it's a lower index or an upper index thing. So that's why I don't worry about that much. And now where does that come from? You see here del I phi is actually del over del xi phi. Now, what does that mean? Kx is ki xi. So del over del xi of kx is actually plus ki. So you see here I have minus I kx. I'm taking its derivative with respect to xi. There is this minus I over here. So it doesn't bring an I times ki, it brings a minus I times ki. So that's my minus sign. So here there is actually a minus sign. So here there is a minus sign. Here there are no minus signs. Now, the last line. You see, these two things commute. Right? So now, if I changed k vector to minus k vector, this thing doesn't change. But this thing changes sign. So the integrand is odd when I replace k by minus k. I'm integrating an odd function over an even interval. So that integral is 0. Okay. So the second integral the integral of an odd function over an even interval. So basically I'm done. So it's this one. So in fact, P mu is d cubed k divided by 2 pi cube 1 over 2 k mu. You see, we had already calculated the momentum. The momentum, instead of ki, we just get the energy. Okay, I will not calculate it. Let me just give you the homework. Calculate the commutator of P mu with phi k and P mu with phi dagger of k. Okay, we already had done it for mu is equal to 0. For an arbitrary mu, it's basically the same derivation. And what we will see eventually, I mean, we already have seen it in the case of the Hamiltonian, phi k acting on a state with some momentum p is a state with momentum p minus k and phi dagger of k p plus k is a state with momentum p plus k. And this is true for, we already have seen this for the energy, the zero component of the momentum, but it's actually correct for any component. Sorry, p. So our interpretation of these phi and phi dagger as particle creation with energy Ek and momentum Pk is consistent, let's say. So that was the aim of this exercise in a sense. Now let us do one more exercise. Let me look at this one. We have the field phi. Let me calculate e to power minus I p mu delta mu and e to power I p mu delta mu. You see, what we said that, and what I claimed was, if I have a symmetry, I have a conserved quantity. If I have a conserved quantity, then I have a symmetry. You see, starting from the symmetry, we had derived P mu, which is conserved. Let's say that we know P mu and we know that it is conserved. What will this give me? How do we know? Let's calculate it. Well, I will calculate it. I will just calculate. I will do the Taylor expansion. I will just calculate the first term for small delta. Minus I p mu delta mu phi of x e to power I p mu delta mu. No, sorry. This is also an expansion. One plus I p mu delta mu plus of the order of delta squared terms, which is phi of x minus I delta mu p mu of phi of x minus phi of x p mu, or phi of x minus I delta mu, the commutator of p mu with phi of x. Now let me, to calculate this commutator, let me just use, I mean, if you like, we can just go ahead and calculate. We know the expression of pi of p of mu. We can just put it over here and obtain the relation. But rather, let's just stick with, we know that p of mu was actually the integral of t0 mu, which was d cubed x, or let me use the y, pi of y, phi that of, let me use the j component only, phi that of x, no y. So p of j, commutator with pi of x, phi of x will be d cubed y. It's just pi of y, phi of x, no. Okay.
Del J phi of
Yes, del j of phi. Del j of phi. Well, del j of phi commutes with phi at equal times. Well, this will be Dirac delta x minus y. So this is just del j of phi. Here there is a minus I. So phi e to the power minus I p mu del mu, phi of x e to the power I p mu del mu is phi of x minus del j del j of phi, assuming del mu is equal to 0 del. I'm just considering space translations. For the case of the time, it will be similar, the derivation will be similar, but somewhat more complicated. But this is nothing but phi of x minus del, up to terms that are proportional to del squared. So you see, knowing this conserved quantity, now we can identify the symmetry. And just note that, I mean, you are most of the time used to using the momentum is equal to the derivative operator. Here it wasn't so. We didn't use it at all. Yes.
Şu en baştaki ifadeyi şeyden önce, tarihine başlamadan önce for small s.
Hı hı.
Bunu nereden tanıdık şey yaptık?
İddia ettim, doğru çıktı.
Yok, şey demiyorum. Small s değil de onun altındaki ifade.
Şunu mu? Bu ifadeyi mi?
Evet.
Well, that's what I say. I mean, I said, let's look at that expression. And what we actually have proven was this is equal to phi of x minus del. This was the symmetry that gave us the conserved momentum, p mu.
actually it is
P mu is written in terms of quantum fields. Now you can also write it as a derivative. I mean,
Can we say the P mu generator of the translational symmetry?
well, that's what we say. You see, this is what we say. I mean, if you have any symmetry, let's say U, the question is how does it act on your fields? Usually the action will be U phi U dagger. And in the case of translational symmetry, U is e to power minus I P delta. That's what I use. Now that's why I looked at this expression, this one, because I knew the answer.
I can't understand. We can write this expression in classical fields for classical fields.
Okay. So what can't you?
Can we write it?
Well, for classical fields, can you write it? Yes, but the thing you have to be careful about is the Poisson bracket. You have to somehow convert this expression to an expression that will be involving the Poisson brackets. You see, that expression over there. You see what we had shown, that this was phi of x minus I, okay, did I make a sign mistake somewhere? Pi and phi commutator is minus I, right? Yes, it's minus I. So here I have a minus I. No, okay, that's fine. P delta phi plus 1 over 2 minus I squared P delta phi plus 1 over 3 factorial minus I cubed P delta phi. So if you just expand it to all terms, this is what you would get. Well, since in quantum mechanics at least we are saying that these are operators and these are just the commutators, I can nicely combine all this expression into such an exponential. In classical mechanics, these are not just the commutators, they are Poisson brackets. So if you define this action to be equal to this one, then you can do it. So all these brackets in classical fields will be Poisson brackets. So formally, I mean, you cannot really write them as U phi U dagger. I mean, that's not the ordinary product, let's say. You should define some new kind of product using Poisson brackets. If you pay attention to that, yes, it's also valid in classical physics. Yes, any questions? So the lesson up to this point is, well, we can write down these fields, we can quantize these fields, and we can identify these as particles with given momentum and given energy. And up to here we were dealing with only the free particles. Okay, now what about interactions? What happens if we have interactions in our picture? Let's look at interactions and let's look at perturbation theory. So, okay, so let's say that we have our formalism somewhat for at least for free scalar fields. Now, when we turn on interactions, what would you be like? What would be interested in calculating? Eventually, we will be looking at how certain quantities will be changing with time. We will have some states, let's say created at some time t is equal to t0. We will let them evolve. At least in the Schrödinger picture, this evolution is given by our Hamiltonian. And then we will have some operators corresponding to some observables. And we will essentially be looking at these quantities, their expectation values. And we had already discussed that, okay, on one hand we have the Schrödinger picture, which says that, okay, let's just combine these things as time-dependent quantities. And the operator doesn't have any time dependence, of course, unless it has some explicit time dependence. And then we have the Heisenberg picture, which says that, no, let's leave the fields as, let's not touch the fields, they don't change in time, but let's just take all of these as our time-dependent quantity. And using this prescription, you can actually calculate whatever you want. And you can even calculate within this picture, let's say you have a given state, what is the probability that at a later time it will be in some other state? Let's say that if at a time, let's say, what is the probability that it will be in the state phi at the time t? But that probability is actually this one. So in that case, this is your operator O. So you can also describe those probabilities within this picture. Now, what happens when you have perturbation theory? Okay, this is correct, but the problem is we cannot usually solve this. For an arbitrary I, H, Hamiltonian, the solution will not be possible. But we will still have the Hamiltonian. We will still be able to separate the Hamiltonian into two parts. One is a part which we will assume that we can solve, H0, and plus the additional term, whatever that term is. And this combined term we will not be able to solve. Now, what we are hoping to do in perturbation theory is we will first start from an approximate solution, and then starting from this approximate solution, we would like to add some corrections to it. So we are also looking at time evolution of our system. Now, in this case, since we have also this V term or the potential term, the evolution will be influenced by both H0 and V. But H0 we already know. We would like to somehow separate the evolution with respect to H0 and the evolution with respect to V. So those two things we would like to separate. So what we will do is, okay, we will evolve the operators themselves, as in the Heisenberg picture, using H0. That is, we will say that the operators evolve as if there were only H0. But then there's the influence of V. Well, we will take into account the influence of V by a time evolution of the states. Now, why do we make this separation? Well, you see, the operators, whatever state you have, they are the same. You use the same operators. So we can take into account the evolution of H0 exactly. And then we will take the evolution with respect to V as a separate perturbative, in a perturbative manner. Okay, let me try to make it more clear. So this is what we are trying to evaluate at the end of the day. Whatever picture you use, it doesn't matter. This is what I would like to calculate. Now, let me write it in a slightly different way. I have the operator O. Let me evolve the operator O with H0. Since I can solve H0, I know what these operators are. Well, of course, I shouldn't change the other parts. You see, this is just identity. And similarly over here, I just inserted the identity. And in fact, if you look at this term, this is equal to identity if V is equal to 0. Because if V is equal to 0, H is equal to H0. So that's just the identity. So the trick will be essentially to calculate that thing, this thing, as a Taylor expansion in V. If V is small, its deviation from identity will also be small. So this is what we call the interaction picture. In the interaction picture, the operators, this is how we define the operators. And in the interaction picture, this is how we define the states. Remember, this is the state at t is equal to t0. Essentially, I pick up a reference time, t0. And this is how it evolves in this interaction picture. Let me give this a name, this whole thing. U of t, t0. Let me see how it changes with time. You see, what I would like to do is I would like to calculate this u as a perturbative expansion in V. Well, rather than trying to calculate that product of exponentials, let me try to find some differential equation that u satisfies and try to solve that differential equation. And we already know the boundary value, u of t is equal to t0, this should be equal to 1. The identity. Well, let me take the time derivative of u. This will be IH0 e to power IH0 t minus t0 e to power minus IH t minus t0 plus e to power IH0 t minus t0 minus IH e to power I minus IH t minus t0. Well, I can also write this as e to power IH0 t minus t0 minus I h minus h0. You see, it doesn't really matter whether I write h0 in the front or in the middle, because h0 commutes with this exponential. And it doesn't matter whether I write h in the middle or at the end, because h0 commutes with the second exponential. But I just cannot write h at the front, because h need not commute with h0. Or I cannot write h0 at the end, because h0 need not commute with h. But I can write both of these h0 and h in the middle. So this is what I would get. Well, let me also insert an identity over here. But you see, this is h minus h0 is v. Operator evolved under h0 in the Schrödinger picture is just the interaction picture. So this is derivative of u with respect to t is minus I v in the interaction picture t. And this over here is nothing but u. T0.
Why we commute the h and h0? Why can't commute?
Because it depends on whether v commutes with h0 or not. It need not commute. For example, v can be, just consider the harmonic oscillator potential. V can be the harmonic oscillator potential and h0 is just the kinetic energy. They don't commute with each other. So that's why I cannot assume that h and h0 commute with each other. In general, they will not. Of course, under certain special cases, they might commute, but in general, they will not commute. But even if they commute, this last expression will still be valid. Okay, nice. So how do we solve this equation? Well, I can just convert that differential equation into an integral equation. Just integrate both sides. Let me put a t prime over here. From t0 up to a final time t. The left-hand side is u of t0 minus u of t0. This should be equal to minus the integral from t0 to t I vi of t prime u of t prime t0 dt prime. But this, we know the boundary condition, this is just 1. So u of t0 is equal to 1 minus I from t0 to t dt prime vi of t prime u of t prime t0. This same thing I can write as 1 minus I from t0 to t. Instead of t prime, let me use t1. vi of t1. Well, here I have u of t1 t0, but u of t1 t0 is just 1 minus I integral from t0 to t1 dt2 vi of t2 u of t2 t0, or u of t t0 should also be equal to 1 minus I from t0 to t dt1 vi of t1 plus minus I squared from t0 to t dt1 from t0 to t1 dt2 vi of t1 vi of t2 let me just compress them a bit. Times u of t2 t0. Well, u of t2 t0, I can just again do the same thing and replace it with this expression over there. So this should be also equal to 1 minus I t0 to t dt1 vi of t1 plus minus I squared from t0 to t dt1 t0 to t1 dt2 vi of t1 vi of t2 plus minus I cube. Well, let me just move it down. dt1 t0 to t, t0 to t1 dt2, t0 to t3, t2 dt3, vi of t1, vi of t2, vi of t3. And, well, you can guess the next term, minus I to the fourth, 4 integrals, 4 factors of v. Well, in this form it is correct, but I mean it will not be so easy to write it down all the time or to manipulate it. But let's just note one thing. Let me look at the first this term only. From t0 to t1, t dt1, from t0 to t1, dt2, vi of t1, vi of t2. Well, it would have been nice if the second integral also goes up to t, right? So because it would be nice, because if it would go up to the t, this would be nothing but dt vi of t from t0 to t square. But there is a term missing. You see, if I want it to go up to t, I need to add from t0 to t dt1, from t1 to t dt2. This is the term I have to add to obtain this one. Now let me change integration variables. Now change the order of integration. Do you know how to change the order of integrations here? So this will be, let's say, dt2, dt1. Now you see, t2 is always, t2 goes up to t. The minimum value of t2 is t1, but the minimum value of t1 is actually t0. So t2 can go from t0 to t. But t1 is always less than t2, because t2 goes from t1 to t in the first integral. So t1 is always less than t2. So t1 goes up to t2. Now let me also change the name of the integration variables. Let me just name t1 to t2 and t2 to t1. Just the renaming, nothing else. Well, you see, remember, the actual term we have is this one. From t0 to t dt1, from t0 to t1 dt2, vi of t1, vi of t2. This is the actual term we have. The term if it would turn out to be this simple expression, we want to add this one to this term. Because if we add the last term on the previous page to the first line in this page, if we add them, then the integral will be, both t1 and t2 integrals will be from 0 to t. But you see, those two terms differ only by the ordering of v. So I have to somehow commute the vi's at different times. But vi at equal times they might commute, they will commute, but at equal times they need not commute. You see, we had already seen an example in the Heisenberg picture last week. We looked at the commutators of the position at different times, and they did not commute. Similarly here, Vi of t at t1 and Vi at the time t2 need not commute. So I will invent something. I will make a definition. This will be equal to if t2 is less than t1 and Vi of t2, Vi of t1 if t1 is less than t2. This is what we call the time ordering operator. Okay, we do multiply the operators, but in such a way that the operator that has the earlier time acts first. Now let's go back to our initial expansion. You'll see here. Okay, here there are no operators at different times. Here we have products of two operators, t2 and t1. But remember, t2 is always less than t1. So this product is actually a time-ordered product. Here, t3 is always less than t2. But t2 is always less than t1. So t3 is less than t2, which is less than t1. So this product of three potential operators, they're already also in time ordering. So this expression of u is also valid whenever if I replace all these products with the corresponding time-ordered products. Well, here there is a single operator, but by convention, I will define it that to be just itself, and similarly over here. Now, what do I gain by doing this? Again, let's look at this term, the first term. Now, what we wanted to add was this term, from t1 up to t. And we had seen that this is actually equal to from t0 to t dt1, from t0 to t1 dt2. Well, the time ordering is still there. Vi of t2, Vi of t1. But you see, inside the time ordering, it's the time ordering operator that determines the order of the operators. So I can easily exchange their position inside the time ordering. The result will not change. So this is actually equal to from t0 to t dt1, from t0 to t1 dt2, time ordered operator Vi of t1, Vi of t2. Well, what does that give me? So what we actually have is this one. This is what we actually have. But so we have this one, t0 to t dt1, t0 to t1 dt2, this time ordered product, plus, well, let me just add the term from t1 to t. Well, in fact, let me just add the same term. T0 to T dt1, T0 to T1 dt2, time ordered product. It's the same term, but I can replace this one just using this identity over here. This one is actually equal to, from T0 to T dt1, from T1 to T dt2, time ordered product. But if I do that, what I obtain is just 1 over 2 from T0 to T dt1, from T0 to T dt2, time ordered product of Vi of T1, Vi of T2. Well, this time ordering product, I had defined how it acts on products of operators. I will just define it to be a linear operator also. So if I have the sum of operators, and I'm talking about the time ordered product of the sum, it will be just the sum of the time ordered products of each one of those terms. But that tells me that I can take that time ordered product out of the integral sign. And this is equal to 1 over T time ordered product of from T0 to T dt1 Vi of T1 squared. Keep in mind, what I'm doing is I'm just writing the initial expression in a slightly different form, which is more familiar to us. Just don't take this definition too formally. Because one problem is, you see here, we are talking about the time ordered product, but if you have any function and if you evaluate that function over time, it doesn't depend on time. So in that sense, this term only makes sense if you first write out that product and then move the time ordering operator inside the integral. Only in that case it makes sense. Okay? Okay, now let me put a factorial over here. It's the same thing. Okay, I will not repeat the same procedure for the other terms. But let's see, we had this expansion over here. This is u of tt0. This is equal to 1 plus time ordered product of minus I integral from t0 to t of dt prime Vi of t prime plus time ordered product minus I squared over 2 factorial. This is the term we had actually studied, from t0 to t dti Vi of t prime squared plus time ordered product 1 over 3 factorial minus I from t0 to t dt prime Vi of t prime cubed. Let me write the next term also. Can you guess the next term? 4 factorial minus I t0 up to t dt prime Vi of t prime to the 4th power, etc. Again, just I will use the time ordered products linearity, which I define. I'm just defining this t thing to be a linear, and it just orders the operators according to their time. But then this is nothing but if I just take everything in time inside a single time ordering operator, the whole thing is nothing but the expansion of the exponential, time-ordered exponential of minus I t0 to t dt prime vi of t prime. So this is our u. This operator u determines how my state evolves in time from t0 up to t. Any questions? Well, let's look at some of the properties. Well, let me, okay, this is from our reference time to the point t, but we can just generalize it. From any t1 up to t2, it is just a time-ordered exponential of minus I from t1 up to t2 dt vi of t. And you can just write down some properties. Let's say u of t1 to t2 u of t3 to t2. This is the time-ordered exponential of minus I t1 t2 to t3 dt vi of t times time-ordered exponential minus I from t1 up to t2 dt vi of t. But this is nothing but, okay, you see the first term has only operators between the times t2 and t3. Okay, I will be assuming t3 is larger than t2, which is larger than t1. The first term has operators between the time interval t3 and t2. The second factor has operators in the time interval t1 and t2, which is earlier than any operator between the interval t2 and t3. So if I put both the exponentials under the same time ordering, I will not be changing ordering of the operators. So this is exponent minus I t2 to t3 dt vi of t, exponent minus I t1 to t2 dt vi of t. Now, since these vi of t's are operators and they need not commute with each other, in general I cannot combine the exponentials. For operators, e to the power a times e to the power b is not equal to e to the power a plus b in general. Sometimes they are, but most of the time they are not equal. But here all the ordering is done by the time ordering operator. So inside the time ordering operator, I can just change the ordering of the operators because the actual ordering is done by the time ordering itself. So this is equal to time ordered exponential of minus I from t1 to t3 vi of t, which is u of t3 t1. By the way, what does u of t2, t1 do? What's the meaning of it? Well, using this property, we know that u of t, let's try to prove it this way. U of t2, t0, I know what that is. You see, I had taken my reference time t0. That is when the interaction picture states and the Schrödinger picture states and the Heisenberg picture states, they all match, they are all the same. And u t2, t0, t2 just evolves my state in the interaction picture. But this is also equal to u of t2, t1, u of t1, t0. So if I just put it in a state u, t2, t0, psi t0, this is equal to u of t2, t1, u of t1, t0, psi of t0. But the left-hand side is psi of t2 in the interaction picture. The right-hand side is u of t2, t1 times psi of t1 in the interaction picture. So this u of t2, t1 does actually evolve my interaction picture states from the time t1 to the time t2. Okay, nice. What is its explicit expression? Well, let's try to calculate that. You see, this u we had defined as e to power I h0 of t2 minus t0 and e to power minus I h t2 minus t0 psi of t0. Or in fact, I might directly use this expression to determine what u t2, t1 is. Well, the left-hand side, e to power I h0, t2 minus t0, e to power minus I h t2 minus t0. This is equal to u of t2, t1, e to power I h0, t1 minus t0, e to power minus I h t1 minus t0. Well, let me multiply from the left by e to power I h t1 minus t0 and e to power minus I h0 t1 minus t0 from the right. So on the right hand side I will end up having only u. This is equal to e to power I h0 t2 minus t0, e to power minus I h t2 minus t1 and e to power minus I h0 t1 minus t0. It's not exactly similar to the expression of u of t2, t0, which was e to power I h0 t2 minus t0, e to power minus I h t2 minus t0. It's slightly different than that. Okay, nice. So, okay, what do we know? Okay, any questions up to here? Okay, so now we have the definitions that we will use. Now, what are we interested in? is eventually we will be interested in doing how the particles scatter off each other. So for example, or how the particle goes from point A to point B. So what we will be interested in is, let's say we have our vacuum. Note that I don't use the zero, because now I'm looking at an interacting theory, and this is the ground state. I don't know whether this ground state contains any particles or not. So I just use it a different symbol. This state is the state that is annihilated by all the annihilation operators. So that state with zero doesn't contain any particles. So that would be my ground state if there are no interactions. But if the interactions are negative enough, the ground state might contain particles because their interaction will create a negative energy. So I don't know, but just for the sake of being on the safe side, I use a different symbol. Okay, that is my vacuum, the ground state. Then I would like to create some particles, let's say with momentum, or at the point x. I create some particle, then I let it evolve in time. So its evolution will be e to power minus I h t minus t0. This is at the time t0. That is my initial state. I let it evolve and then ask the question, what is the amplitude that I will be able to observe it at the point y? So this is a particle at the position y at a later time. Or I can write it in this form, omega. At the end of the day, these are the things I would like to calculate. At the time, initial time, I might ask the question. Initially, I have two particles, so I have here two creation operators. Then I let my system evolve, and then I ask the question, what is the amplitude that I will have two particles at x3 and x4? So initially, I create two particles at the points x1 and x2, and then I ask the question, okay, what is the amplitude that I will have two particles at the point x3 and x4 at a later time t? Or you can also do the same thing. You create particles with definite momentum. That's what we do in experiments. We create particles with precisely known momenta, maybe not exact, but good enough. And then ask the question, what's the probability or what's the amplitude that at a later time we will observe two particles with momenta k3 and k4? That's the question we are interested in. Now I can convert all of these into my interaction picture. Okay, there are two things I need to do. Okay, one is, how can I relate omega to 0? I would like to be able to write one in terms of the other one. Why? Because I know the properties of 0. I know 0. I know the no particle state. I know how my operators act on it. I don't know what this omega is. So if I can express omega in terms of 0, then that would be great. Then I know how everything acts on 0. I know how my states will evolve under H0. And I will also know how to do a perturbative expansion of the evolution of the states. So that is where I'm kind of heading to.